I'm thinking more people will show up, but they do and they do. So, this is Cliff Click, Coffee Compiler Club, anything to do with compilers and language runtimes and garbage collection and performance and GC and locking and concurrency and yada, yada, all's fair game. Mute your mic if you're not talking, which everyone is. Open mic, reserve the right to moderate, never had to. Theory says I'll get it up on Twitter within a day. If you don't like being videoed, get out. I have to say this because my lawyer thinks he told me so. Done. And after that, I'm going to do a little progress. And then I know, York, you were talking about last week, you wanted to say something. I don't know, we never got around to whatever you were at. So,
yeah, I mean, I always have plenty of stuff to talk about.
There you go.
Yeah, I can start, I guess. Let me see. Yeah, so the thing I've lately mostly been working on is redoing the implementation of my concurrency implementation in Inco, combined with some other stuff that I want to do.
Inco, what's Go?
No, Inco, the language. Sorry.
Okay, thank you.
Because it used to be like Erlang, as in you can send and receive messages to actors at any arbitrary point in time. And I've been trying to make that type safe for quite some time. Now on the sending side, that is possible. Like if you parameterize the object that you're using to send the messages, that is doable. But on the receiving side, it's basically impossible, because at any point you can do receive, so the compiler doesn't really know, what actor it's currently running, what types of data that one can handle, etc.
It's like a big switch you want. Here's all the types of everyone who ever could open a channel.
So the way you do it in Erlang, for example, is you do receive and then you have to apply pattern matching on it. And it will retain any messages that don't match. So then later on, whatever code wants to use that can still match on that.
But you're not required to match on messages that might get sent to you.
No, so you, so the mailboxes are all scoped to the actors. So you won't get a message sent to another actor, but you might get a message that's meant to be processed later on in your actor.
Right. What I'm asking is it possible for you to send a message of a type that the receiving actor doesn't know, doesn't pattern match, and will never, because he never pattern matches, will never pick it up?
So in Erlang, I believe that is possible. So your mailbox can overflow. Unless
unprocessed messages are allowed by the typing.
Yeah.
Yeah. Okay.
And so in Inco is kind of similar, where when you send, you just put it in a queue, and that's basically it. The challenge there is that my pattern matching is much more limited. Like in Erlang, you can do destructuring and all that stuff. In Inco, you can't do that. So it's basically just a pain to work with. So I'm now working towards a setup where the concurrency model is much more like remote procedure calls, instead of just arbitrary data that you send to some actor. So essentially, you in my current sketch, you define a class as being async, which then allows you to define async methods. And the general idea is that when you create an instance of such an async class, it will actually spawn an actor. And that actor will run the it has access to the inside of that class, basically, and its variables, etc. And then the outside can only use these async methods. And they in turn return a future, and then you can wait for the results, check it, whatever. But it retains the preemptive scheduler that there is currently. So if you wait for a future's result, it will block the actor, but not the OS thread. So you don't have to mess with callbacks and all that stuff. It's the model is sort of loosely based on a language called Pony.
Yeah.
Let me add that to the chat. They do something similar. They have it a bit different, where they call it promises, even though technically I think they are futures. And they use callbacks because they don't want to block
right
at any point. And I think yesterday of all this work, I finished the VM side of things. So, changing all of that was quite a bit of work.
Mm-hmm.
I haven't changed my compiler yet, so I have no idea if it actually works. But it's the underlying idea eventually is that the messages you send, because they are basically methods in disguise, the compiler can actually check like, hey, does this actor support this message, etc. And on the receiving side, you don't need to do pattern matching or anything like that. And it works with generic types, which is because of type erasure isn't really possible in the old approach where you can just send data across everything. Well, unless you explicitly typecast it. Yeah, that's basically what I've been up to for the last 2 weeks, I think.
Mm-hmm. Yeah, I kind of messed with the async stuff for a while in other languages and never bought into it. It's fine.
Yeah,
Like
it
it's some.
is.
Go ahead.
It is a bit different from the usual async await that you, for example, have in C#. Well, all the more recent languages are starting to add it. In the sense that, for example, from the caller perspective, it looks like just a regular method call. There's no additional keywords necessary, etc. And when you define the method, crucially, you don't have to say, hey, the return type is a future or this or that. You just say, the return type is an integer, and then the compiler will transform that, much like generators, to the appropriate calling convention, basically. And the end idea is basically you take a class, you just dump the async keyword in the right places, and off you go.
Right. I was trying to sort out. So are the compiler going to be able to cross actor optimize? The obvious problem is overheads. Nice model, high overheads for very cheap function calls. Hey, give me current time noise or whatever, right?
Right.
And then the obvious solution is to inline for trivial cases. And is that still possible?
Yeah, so I would imagine eventually, because inlining, well, any optimizations I currently don't apply, but
Fine.
Inlining of async methods, I think, won't be possible because you're not calling method directly. The way it currently works, basically, it looks up the method, copies the arguments to the target actor, and then stuffs that all in a mailbox.
Yeah, okay.
So that can't be inlined. One idea I had is that if a actor calls a async method on itself, the compiler will just turn it into a normal method.
Right.
But I haven't really figured out yet if that's going to be all that useful.
Right.
And I can see it being a little confusing even.
So you said from the caller's perspective, it's always synchronous. So is this model just for concurrency control?
No, so the caller by default is asynchronous. So you call, or you send the message, you get a future back, and you can then call get on it to get the actual value, and that will block the actor, making it synchronous. But by default, it's asynchronous.
Oh, I'm sorry. I thought you said it looked like a synchronous call and you didn't have to say future.
Right. Yeah. I think the best way to see it, if you have, say, like an option type in whatever language, usually you call like unwrap or get or something to get the contained value. It's the same idea here. So in that sense, it looks similar. It's a bit different from, say, Rust, where if you have a future and you want to wait for the result, you have to use the await keyword. So you get await space and then the thing. If I remember correctly, at least, or maybe they changed it.
Yeah,
whereas here's just a method.
It's just like stuff you've been working on. But like the thing that got me, I screwed around with this in JavaScript and then flipped over to a React package, React and MobX and one other thing, and suddenly life got a hell of a lot better. And the keyword was a pain in the butt. But you wanted to know any given call was asynchronous or not. So you had to have some kind of syntax to make this synchronous or not, and not by default because you all had trash function calls everywhere. So you labeled it async specially. That's what you wanted to do. And then, yeah, you got a future back. And of course, you didn't have to ever block on the future, which if you failed to, and the stuff I was working on, it was a bug that was uncaught by anybody. And silently, something never happened. You never acknowledged the event, and life sucked. The React stuff kind of took that away and did it better. You didn't have to deal with it nearly so much. I was writing a GUI in JavaScript. The pyramid of death and callbacks. It's fine.
I think in JavaScript, I mean, it's a dynamically typed language, so you kind of have to annotate it. And I think in Rust, you need the annotations because I might be confused here, or perhaps my info is data, but I believe to a certain extent, they use state machines for it, although that may have been generators, so I might be mixing things up. But either way, they don't have a runtime, so they're a bit more constricted in how they can do things. Whereas in my case, I have a preemptive runtime, so I can just say, oh, this blocks, put it off to the side.
Yeah, fine. Yeah, okay. Well, I have a bit of progress I want to report. That's sort of progress, I guess. A couple weeks ago, I was very excited to have Henley Milner and forward flow typing integrated. And I've come round and round and round and round and gotten a lot more hardcore about testing. And I think I'm not quite as far as I thought I was, but I'm a lot more confident about where I'm at. So I have an incremental version of Henley Milner that monotonically makes forward progress, I think in linear plus whatever inverse Ackermann's time for the union find behaviors. And I'm fairly confident that it can be integrated with forward flow in a monotonically forward moving fashion, but I'm unclear if I have an incremental version. And so I'm backing off from the forward flow and Henley Milner being both integrated incrementally, and instead doing forward flow to a fixed point and then applying Henley Milner, and that will allow me more forward progress, which will be quick and incremental on the forward flow typing. And then, but when I go back to Henley Milner, I'll possibly have to redo it from scratch. So I don't want that loop to go too many times. I'm going to stack up runtime in an ugly way. But yeah, I've got a Henley Milner that's not the standard tree walk, that is work list, can be done on any portion of the tree in any order, and monotonically makes forward progress to the end. It's not as where I wanted to be, but it was a reasonable cut towards being completely incremental, so I could apply it in an incremental algorithm elsewhere. The trick that I don't have figured out really is an incremental way. When forward flow says I can now take this information and do something with it, and he changes the graph, changes the program. Basically, it's abstract interpretation. Changes the program. I don't know how much Henley Milner has to be redone. That's the piece I haven't figured out, how to actually make it incremental. And so that's sort of my next goal here, is to get hardcore about testing, making mutation changes, and then seeing if Henley Milner will walk forward steadily as opposed to decide it went backwards or whatever. There's a giant n squared assert I'm throwing in. Actually, I have it, and I'm throwing it in. That just retests from scratch versus the incremental side of things. Penguins versus urinals. They're one above each other. It's pretty funny. Fine. So yeah, that's my progress or lack thereof. It's progress, in that I'm now confident that I have a correct answer and I can integrate it, and there's a meaningful fixed point to be had that's sort of monotonically better than either one alone. that, and I pulled up my thesis, and pretty much that technology will apply in the top-down version as well. So there is a step there that says I'm going to re-implement my thesis using Hindley-Milner for the integrated top-down version with forward flow typing, and that will be should be one pass incrementally correct, the same incremental I got with the bottom up. I just haven't figured out how to do the bottom up with graph rewrites. Like the top down one doesn't do graph rewrites at all. It takes a frozen program and then computes best effort typing. But the bottom one can edit the graph, edit the program on the fly as it goes. And what I don't have is how to incrementally edit Hindley-Milner, specifically around inlining, which clones code and gives you more precision. So that's my progress. All right, somebody else's turn. I'll make Cameron talk about, Yorick talk about async await versus Cameron's model. That's what I was trying to get. You missed by 2 minutes, Cameron.
Sorry to hear that. I just lost track of time.
That's okay. I did too. My slow start today.
How's your wrist?
It's really good. I mean, it's in a cast, but it's doing great. I'm healing.
Good.
I'm still, you know, I put a bread bag on it to take a shower, but other than that, everything's fine. Still going to the hot tub. Still ski.
Right there.
Yeah.
So what's the so tell me about this async await.
Yeah, I'll recap it quickly. The old model that I was using was Erlang based. So at any given point in time, actors can send and receive messages, and to make that anywhere close to type safe requires extensive pattern matching on the receiving end. I got a little fed up with that, and inspired by how Pony does concurrency, I changed the model so that messages are now essentially remote procedure calls. They do happen all on the same OS process. Distribution isn't really something I'm currently interested in. And when you call a remote method, basically, or an async method, you get a future back. You can then wait for the result or not, in which case it's asynchronous. And waiting for the future only blocks the waiting actor, not the underlying OS thread. So it ends up basically looking like method calls with the type safety guarantees of that.
Right. Yeah, I like it. So you said you can get a future back. What's the alternative?
So in my current idea, you always get a future back. I'm considering perhaps that if the method returns nothing, that the remote call also returns nothing, because waiting for a future that doesn't produce anything isn't particularly useful. I haven't implemented it yet, but basically by default you get a future, and you can completely ignore it if you want. You can wait for it specifically, or you can poll for one or more futures.
Right.
In which case the same semantics happen. Like, if one is not ready, it will pause the actor, and once it's ready, it will reschedule it.
Yeah, I think there are three things to consider with asynchronous calls. And the first is completion. The second is return value. And the third is any error handling, if that is in addition to the return value, like an exception, for example. So the reason to get a future outside of a return value is the other two of them, which is to say, if the caller wants to, for example, call 5 async things and wait for the completion of all 5, that might be an example. Or if the caller needs to be able to say, if an exception occurs, do something. But those are the three things that I've seen related to the async calls.
Yeah, exceptions I still have to make a decision on.
I strongly encourage you to demand that every future that gets made must get waited on, and at the wait point, and that's your exception delivery.
Right. Well, so the idea I had in mind is that the way the futures are currently implemented is basically a single producer, single consumer queue. It's not really a queue; it's just a single field that it writes to, but it's a similar concept. So what I was thinking is either the async methods can't throw. The language already has this sort of support baked in, so that would be fairly straightforward, but it would also be pretty limiting. The other option is that they can throw, at which point you have to tag them. And then the future is also tagged with the error type. And then in my language, that forces you to handle the error. I applied this model similar to generators, where if a generator doesn't throw, no error handling is necessary, because the generator type is generic, as in it contains the value that it yields and a parameter for the value that it throws, which defaults to never, which means it doesn't throw. I could do the same thing for futures, and then if error handling is necessary, the compiler will force you, and otherwise it won't. And because it's part of the type, it's not something you can accidentally lose. But I don't have any facilities right now to say, hey, this variable, for example, if it's a future, you must use it in some way.
So doing a bunch of asynchronous computation in H2O, so big clustered parallel computation, people write broken code, exceptions happen that are stupid runtime exceptions. Debugging was a nightmare until we got cross-cluster throws, and demanded that you had a future get on every future. You had to get it, because that's when your side effects were guaranteed to happen. So if you wrote effects and fields, you produced results that were memory. There was no memory model until you did a future get. So that worked out as a whole. The programming model worked out. Now there were no compiler support for demanding every future got a get. So people would screw that up, and then they would have bugs because they had a race, because the side effect they're looking for, or the exception they were trying, should have happened, whatever, broken in that way.
Right.
So yeah, I don't know what the right model is, but in my head, I'm going to go to definitely demanding that you must do a get if you did an async call.
Yeah.
And then make that.
Yeah. So in this setup, when you would call get on the future, assuming it would throw, that's when it would also surface that exception.
Right. Yes.
And then I think of my error handling is that you can't, if the future were to throw, you can't call get and just not handle the error and have it pop up, say, 5 stack frames higher. The compiler will say, hey, this thing throws, so you must handle it.
Right. Somebody does a array index out of bounds exception because it just blew their math. It's some remote thing, and you have to do something now with the generic exception. So what do you do with array index out of bounds exception right now?
Can you guys hear me right now?
Panic.
Yeah, we're hearing you, and there's a lot of background noise.
It's got the wrong mic then. Shoot. I have my mic off. And I have Zoom telling me, do you have
yes.
professional audio going or something? I'm like, what?
Yeah.
Sorry, let me figure out.
We're hearing
Zoom.
your professional kid do his practice lessons in the background.
Yeah, there's some oboe going on.
Yeah.
I apologize. Tell it to use this mic. External.
Sorry,
yeah, no, so out of bounds are a panic. They currently, the default is they terminate the whole program. Per actor, you can override it so that it terminates that actor.
Okay.
I am considering ripping that out so that a panic is just always a hard termination of the program.
Yeah.
Because there's just too many cases where a panic happens and there's just physically no way you can recover from it.
Yeah, okay. So what's another kind of exception that you might expect?
Did we have the Midori discussion on this a week or so ago?
Yeah, we had a discussion about this a week ago. Yeah. So I'm trying to sort out.
Yeah, this is heavily inspired by it. It was a big source of inspiration.
It's 2 weeks ago, because last week was something else, I think. They all run together. Yeah, like file not found. I don't know. I'm making up shit. right?
Right.
You know, open for read, write, no permission.
Yeah, so that throws an exception,
Okay.
but the sort of Midori style error handling means it can't bubble up unless you explicitly told it to. Setting aside compiler bugs, of course, but
Right. So it can't bubble up means you have to handle it at some point or declare it
yes.
getting thrown.
Yeah. So
can you declare it across a future?
Yeah. So for example, let's say you open a file. You know, the Inco has a method called read only to open a file in read only mode. That may throw, you know, if the file doesn't exist.
Right.
At that point, the compiler says, "Hey, you have to stuff this extra keyword in front of the call so that we know it throws." And then you have two options. You can just either throw it again, at which point the same rules apply to the code that surrounds that, or you can handle it in some way.
You don't have it just flows through. Yeah, I've read this blog before in the chat. You don't have a default, it just flows through, goes uphill.
So it depends. So let's say you tag a method as throwing.
Yeah.
If you just call it as normal, that's a compiler error. What you have to do is stuff the try keyword in front of it. And if you do just that, then it will rethrow.
Okay.
And then the same rules keep applying.
Yeah, it's like the Java runtime exception model is what I'm thinking
checked
of.
exception.
Unchecked, it just kept throwing. You have to do something about it. I mean, in worst case, you checked. Yeah, checked. You're right. You could label the method as on its type that it also throws because it calls a throwing thing.
Correct.
And if your get can throw, then your get can throw, and now it propagates there. That model of taking the exceptions from wherever they came from all your remote async calls, gathering worked out well in practice. You got a decent chance to do decent error recovery at a level that made sense, even if the guy who threw was some remote portion of a cluster.
Yeah, I love the Joe Duffy. It's Joe Duffy, right? Joe Duffy blog.
Yeah, I've read this.
I disagree with his conclusions, but I love his reasoning, if you know what I mean.
Yes, he has the hard and give it up, which I think abandonment, that's what he calls it. Yeah, I think that's a totally fair thing to do. Like you said, runtime exceptions, you're abandoning. You just like, programmer bug, fix your bug, die like a pig.
No. So they're crucially, it is a crucial difference. Like runtime exceptions, at least in Inco, they are things like file not found or.
Well, I'm sorry, I used the wrong jargon word. What do you do with array index out of bounds?
Panic.
Okay, so he has what he calls abandonment.
Yeah.
Panic. Yes, fine. He says there is a class of bugs we agree to panic on. Like in the land of Java, it's generally reasonable to panic on out of memory and Stack Overflow because there's generally not good recovery there. And I have worked with like H2O doing big data. We could sometimes recover from out of memory. We would abort some large calculation and free up gigabytes to terabytes of memory across the cluster. So you would recover really, kind of, because you blew an exception in a bad place. So it wouldn't necessarily recover. Overflow, the only recovery I get out of that is like, I want my debugger to like intercept it sanely and unroll the thousands of rolled stack frames and give me the fucking start ones, because that's when it began the recursive death spiral.
I mean, the reason that Java struggles with this is because it's not hierarchical. All the threads are global. All the memory is global. So you can take any object created on any thread and pass it to any other thread, and it's all global mutable for all practical purposes.
Yeah.
And so the problem with out-of-memory errors is that how do you contain the side effects of the out-of-memory?
Yes, that's what I'm saying. For a particular programming style doing big data math, there is a way to contain it.
And I think
that's not a general, you're right, it's not a general model.
Mark, do you remember with out-of-memory, was that the one that we explicitly did not try to recover from? That was the one that...
the recovery was pretty bad. We tore down portions of a cluster member and then let them restart. But it didn't even mean you got kicked out of the cluster. Like we would restart the service.
But you would let it.
So yeah, we were still pretty tolerant. But yeah, we shot like the thing in the head that saw the out of memory, but like we contained it it wasn't like we took down the JVM. We were much more tolerant than that.
Right. And
Although we then suggested to customers that they configure their JVM that on out of memory, you take down the JVM.
do something. Oh, I see. Do something.
But if you didn't do that, we would handle it, reasonably well.
Right.
But obviously, if you're out of memory and that keeps happening, you're still screwed.
Well, that was one of the biggest problems we had with production outages was that, if you have 100 servers, managing, 50 terabytes of data and you run out of memory on one of them, if you can't handle it on 100 servers, you're probably not going to be able to handle it on 99. And strangely enough, then you can't handle it on 98. And then there's a real problem on 97. And pretty soon Amazon's down. So.
Well, didn't see Amazon going down for us, but I definitely saw. Mostly we would recover in H2O. Everywhere else I just gave up on. H2O I could recover because we would kill some big data computation, and it was usually temporary storage would come back, where the temporary was some very large thing. And that was a reasonable recovery mode. And that would also recover memory on every member of the cluster. So it's a different use case. I think you're right. In general, there's not a good recovery. So you guys have these independent services and you would just kill one and restart it and pray.
Well, that was in Java, yeah.
Yeah. Oh, in the land of Java. So what are you doing here in Ecstasy?
It's all hierarchical. So an out of memory is not a VM level event.
It's a container level event. What
it is a container level event, exactly. And it would have to result in the container dying.
Okay. And then do you typically restart the container at the next time somebody makes a call?
Could do. I mean, containers are controlled by user code. So if they restart, they're restarted by user code in the same way that if they start in the first place, they're started by user code. But what it does,
action to restart it.
Right. So what it does is it gives you a unit of throwaway, and that's what you don't have in Java.
Right. It's a unit of throwaway. I got it out of H2O. And you have it you're at the hierarchical container level. So everyone who had a connection to the container gets it cut cleanly.
Right.
And then if somebody says, but I want this container, I'll take a step to restart it.
Yeah. And yeah, I mean, and what we designed it for was to be able to handle, a massive number of seemingly independent entities, containers, if you will, soaking up, the full resources of a large machine. So we needed to be able to have a portion of it, like an Erlang. I think that was the example given.
Yeah.
But you have to be able to segregate a portion that can fail without any impact outside of that failure zone.
Yes.
So I'm curious in that case, in Ecstasy, how do you handle like a host out of memory error? Because if it's containerized, I would imagine containers have a limit as to how much they can allocate.
So when I say container, I don't mean LXC or anything like that. I meant inside a process. So the way it works is that the allocations into a container have to get approved by the container outside of it. So basically, it's kind of like an operating system where, when you say malloc at the C level, it turns around and almost never talks to the OS. But every 1 in a million mallocs, it turns around to the OS and say it's on Windows. It'll global alloc or whatever it's called this year. So it turns global alloc 32 probably, or global alloc 64, whatever they renamed it to. And then it takes that big chunk of memory and manages it internally. So similarly, a container would turn around to its parent container and get more memory like that. And then similarly, the parent container can come along and grab back memory from the child container. So we actually expect that, a single container can expand within a second from basically nothing to many gigabytes and then expand and then contract back down just as quickly, because that's a typical, I know it sounds really crazy, but when I say typical, we've seen typical workloads where a single request needs 100 terabytes of RAM and then needs nothing a second later, so I'm exaggerating for effect. Yeah,
it happens all the time.
Exactly. And that's the type of workload I'm talking about, where I'm doing some super complex, super customized query. You can think of it as a MapReduce style or whatever, but there's user code inside the big O that involves a user data model being realized and then going away if you'd like to be able to get rid of it a nanosecond later. And so the idea is if you can schedule those, you can then basically timeshare a machine very effectively.
So this gets into resource management, which is always a thing that's sticking in the back of my head forever and a day, which is required for any sort of hard guarantee of performance. So if I have a container that wants to swell to 100 gigs and then back down, 100 terabytes, whatever, 100 gigs, back down, and multiple of these are coming along, and I have a limited resource machine. If they run end to end to end, I have memory to go around. If they run concurrently, somebody has to die out of memory.
That's right.
So where is your level of resource management control?
So, and again, a lot of this, as I've said before, is inspired by Hotspot. It's the idea that, where Hotspot would say, hey, I see, this code is being executed 10,000 times, so I have enough information to make some really good optimization choices. Imagine if you could take that up a higher level and say, I see these requests coming in 10,000 times, and they have the following footprint profile. So you could actually use that type of information as an input to how you handle things like scheduling.
Okay, so I guess I'm looking at a different issue. Somebody comes along and makes a request to high-level container, who hands it off to low-level. Low-level says, I need 100 gigs. So
That's right.
high-level gives the low-level 100 gigs. Somebody
And
comes
then,
along, makes a second request. High-level says, I'm going to hand off to low-level container. Second low-level container says, I need 100 gigs. High-level says, I'm all out. So now what do? You got 100 gig container running, request make a second one. You have a control point because you're hierarchical. You can make a decision with the second container. Delay.
So this one is actually fairly simple because delay is the answer in this case.
Yeah.
The real problem is they both come in and they ask for 50.
Yeah.
And so you use up your 100, and then one of them comes back and says, I need another 50.
Yeah.
Now what do you do? And then the other one comes back and says, I need another 50.
Yeah.
And that's where things have to be replayable, right? You need to be able to kill it and restart.
Yeah. If you're if you're transactional, you can abort one, feed the other one, and hope that he lives within he solves in the 100 gigs and gives it back.
Well, you have a couple choices. That's one. There are lower level choices. For example, you can simply page out the container. So yeah, it has 50 gigabytes, but it's not using anything in memory now.
I would claim, okay, my experience with garbage collection is thou shalt not page. If you page, it's heat death of the universe, no bother.
Oh, no, I don't mean OS level paging. I mean,
Container
basically,
level, yeah, but you have to
serial.
50 gigs and write it to disk.
I'm giving it as an example, right?
No, right, but that's exactly what I'm claiming is the performance model there is kill you for out of memory, take an hour to write memory to disk. When do I
50
declare
50 gigabytes to? I mean, it's a random number, but 50 gigabytes to disk is 16 seconds.
It's not the end of the world. That's what you're saying.
It's awful, but it's 16 seconds. NVMe local.
Wow. There's only the SSD drives, but they're pretty damn common. Well, it just says my memory is the size of my SSD drive.
I think
you're picking an entire unit. Garbage collection is death because you wander the heap on a random order.
That's correct. And that again goes back to the fact that it's all global. So I have a giant heap, and this pointer over here
Yeah,
points to this object over here, which points to this one. You know, it's like it goes, there's no,
you're claiming your hierarchical in virtual memory, which
so
means,
the memory is also hierarchical. Exactly.
yeah, you have a tree.
Right, which then makes it go back to more C style, like swap worked there, right?
Yeah, right. Well, you can't give a timeliness guarantee to
No.
the guy who's getting swapped out.
You cannot.
You could claim that the second man, one of the two can make progress because you vote one of your two containers a loser, and you let the other container run forward. And the loser doesn't die; he just takes a giant hit.
Or one of them dies, right?
Well, that was my question. How do you make that decision? What is your criteria for deciding I'm paging you, I'm killing you, or I'm not, or I'm stalling you until I get memory from somebody else?
Well, those are going to be host level, and I don't mean host as in some magical host. I'm talking about user code. So for us, the host is user code.
So here's this is the exact example I just gave a second ago. The high level container starts number one, who asks for 50, he gives it. He starts number two, who asks for 50, gives it. Number one comes back, says, give me 50 more. Now your options are kill one, kill two, swap one out, swap two out. Or somehow
refuse the 50. Yeah.
Well, yeah, you refuse the 50, and now the guy who gets told no has to make
dies.
Right. His decision is out of memory death, right? Which is maybe the correct answer. I'm asking, what is your design theory, process, concept? Like ultimately there comes to the standard problem of job scheduling that IBM's papers from the 60s are all about, like how you deal with resource management and there is a way to make this work, but if you just hand them out incrementally, yes, you will die and nothing happens or it deadlocks or whatever. What do you do? Right. And is there a like funny money game where I can prioritize people and the higher priority guy gets and the lower priority guy either gets an out of memory?
That is roughly the plan. Yes. What our goal is in our own implementation of this algorithm is to be able to prioritize certain workloads over others. And obviously, I think it's safe to say that revenue is involved in that decision model.
Well, yeah. So somebody's paying money to guaranteed hardcore get my trading algorithm to run, whereas last night's batch, check clearing code, fuck it, as long as it's done by 8 a.m., I don't care, right? And do you have a priority? And so
I don't think it's as simple as priority though, right? Because there's probably going to be more than two paying customers, or more than one, right? So you've got multiple paying customers wanting that. So
if you have a set of resources, same as any job, any market, you have a set of paying customers, you have a set of resources, somebody pays more to get it, right? And if you lie and tell them they each have it, but you don't have enough to support them all at the same time, the lie becomes apparent when everyone grabs for the same piece of gold, right? So how do you break that tie, and how do you explain to people where they sit in the resource management hierarchy so they can decide to take the loss occasionally or pay more money, right? You can't just tell everyone you get it all because there's not enough to go around.
Yeah, the goal is generally to prioritize time first. So when you have a resource constraint, the first thing you do is you slow down if you can. So that would be the paging example. And then at some point, someone has to die. So it's just a kind of a hierarchy of decisions that you make.
Transactional, no one has to actually die. You're just going to restart it, and that's time again. So you just claim more time. Is one of the options is never. One of the time is more time because I'm just going to abort you, get all your resources back, do other things for a while, and then get to you later.
Right.
Okay, now how do you negotiate where my task sits in the queue of other tasks on the cluster? Somebody comes along and says, process A gets to beat process B when there's a crunch time. How is that decision made? User code?
I think that's where there's room for like a fair scheduler rather than like priority based, right? So the over time, everybody makes it through.
Yeah, so the
And
problem
like,
with your scheduler, as soon as you said scheduler, is immediately you've decided this is the oracle that decides who gets what. And I don't like the scheduler because he's going to shoot me down, and I want my high priority, and I'm paying all the bills because I'm the high frequency trader dude. So how do I pay my money so the fair scheduler is fair to me and everyone else sucks it?
Yeah, I mean, that's what we're building.
Yeah, I'm asking, what are you doing? You're building a system where it's not a fair scheduler. It's somebody's paying money to beat their buddy across the street. Now, it might be the firm across the street, and it might be the department down the hall, but somebody's going to have a way to distribute funny money that you get a prioritized order.
Yeah. So let me, while you guys are talking, I'm gonna send you a link to one of the interfaces used for this.
This is like one of your.
So in my non-ecstasy day job, I've been writing a fair schedule, and I haven't applied it to memory, but that's one of the things I've been looking at. And nothing gets like this mega priority boost, but then you can say, yeah, like I do want to deem some things more important, right? So you get to like kind of hint that, yeah, this thing's more important, but still over time, like everybody gets to go through the system, even if you were tagged as low priority. Eventually you're owed your time. So I think the same thing can be applied to memory. Eventually you're owed your 100 gigabytes.
So Azul did the memory thing, did the thing where you at launch time, you got to demand X amount of memory. And that was whoever launched you told the priority to the system, and the system would refuse to launch a collection of people such that if they all demanded their max memory, there would not be enough to go around. But then you could also ask for extra memory beyond that was not part of your demand set. And then that would share as best effort, because most things would be launched saying my max might be 10 gigs, but in practice, I only use 1.5, and I never get above that. And it's all heap, GC driven, right? The GC would demand double memory to cut GC costs in half, but you got what you were demanded on launch time. And if there were spare to go around, GC would share. And in this case, we could demand getting memory back from somebody. So we loan memory out from the general pool that would be hard allocated to somebody who's not using it. Loan it out so somebody can make faster GC progress. But if the guy who demands it wants it back, then in one full GC cycle, which would be 10 milliseconds in the worst case scenario, you had to roll your heap back. And you had 10 millis to do it. And in general, the Azul collector could do it. But if it couldn't, you got hit with an out of memory and you got killed. And that prioritized list was given at launch time for the processes. So there was a hard.
These were like in the individual JVMs running within the Azul box.
JVMs was the unit of actor here, if you will. And an individual JVM could be demanded to give up memory in a fairly short period of time. Typically, so many pages had to give up, and that would be so many runs of the GC migrating people, collapsing pages, defragmenting pages. If your heap was such that you were using it and it was all live and you couldn't give it back, you got hit with an out of memory because you were above your, you when you launched said, I only demand 1 gig, but I'm happily using 10 right now. If you
and would it get harsher than that? Like,
sorry?
would you kill that? Would you kill the VM if the out of memory wasn't sufficient to?
So at launch, let's call the bad boy VM1 here. At launch, he says, I only need 1 gig. While he's running, GC says your life set's growing. I go to the system, keep asking for more. I'm using 10 now. But at launch, he's only guaranteed 1. Somebody else comes along, says, I want the rest of the memory in the system, including the 9 that you were given but not promised. Right? So now that's a hard request. He has to give up 9 gigs. His heap is not fitting in 9 gigs. So he lied at the command line when he said, I'll live in 1. He's not living in 1. He's living in more than 1. So that's a kill. So you kill him and get his 9 gigs back. On the other hand, if he's using 9 because he had a big swell in memory and it shrank back down, but his life set is all scattered throughout the heap, it can be compressed down to 1 pretty quickly. And then the 9 gigs get taken away and handed to the other guy, and he's back to the 1 he was guaranteed at launch time. So that was the model. The hard guarantees would fit within the box. The soft guarantees could be taken away at the cost of a GC cycle compressing pages. And if you didn't fit in your hard guarantee, you got the axe.
So I put a link into the chat. So to give you, it's a link to the container control interface. But the what you can see here, if you scroll to the very bottom, you'll see that you can get a kind of point in time view of the
Sorry.
entire container's utilization, etc. But the interesting stuff is actually around this limit memory and limit compute
What line
method,
number?
400 and 419. And the idea here is that you don't want user code generally involved in these decisions. So it sets just the boundary conditions. So for example, limit compute sets a boundary condition. And until it hits that boundary, no user code is involved in the decision making. But when it does hit the boundary, it invokes the provided function, which is obviously user code. And at that point, the user code, which is the code that created this container, since it's the one controlling the container, it has a decision to make. So it can call back in and say limit compute again, which says, okay, you can continue for this much more allotment. So you can think of this, for example, as a time-shared tick implementation, where you would give it, 10 millisecond increments, you would give it the ability to execute. That'd be your worst case use of this functionality. Same for limit memory. You could say, okay, I'll let all of these containers have a gigabyte of memory max, right? But if one of them needs to exceed it, then call me back. That's line 419, right? And at that point, I can call the same method again and say, okay, that's fine, it's exceeding it, but now I'm going to limit it to 10 gigabytes, right, or whatever the. So basically, the design of this was to allow user code to model the shape or the orchestration, if you will, of the various containers, but yet not have user code in the. I'm going to date myself. I don't want user code as a side effect of int21h, right? So I have, yeah, you know what I mean. In other words, when I'm in an interrupt, I never want the user code to run. So what you see is at each of these API points, it's like the interrupt has already kind of set aside the execution. Then I go back to user mode and say, okay, what do you want to do? So I'm just asking it a yes, no question, or a go left, go right question, or how big question, right? How big, how much?
So let me make sure I understand the model here. There's a parent container. He's managing several children. The child starts with a limit memory of 1 gig, has run it out. He calls the parent saying, give me 2 gigs. The parent says yes, and here you go. Later, the child wants to do it again. Where's the callback happening? The child asynchronously, from the child memory allocation point of view, calls
right.
memory.
So child says, new string, hello world, or whatever,
Right.
So does some minor allocation that just happens to be the straw that breaks the Malik's back, right? So it's as if that entire container freezes for a moment while the call is made to
the parent.
max RAM exceeded.
Okay.
Max RAM exceeded is the callback that was provided on line 419 previous to that child container running.
Yeah.
Right.
Okay.
So the child container is momentarily paused because we have to make a decision. We're either going to kill the container because it's run out of memory,
or
that's your out of memory error, or give them more memory. Exactly.
Yeah.
So we have to make that decision. If we give them more memory, all we do is we make a second call to limit memory. And we say, okay, container dot limit memory 10 gigabytes for the max and
Okay.
and then call the same function back again if that happens. But in the meantime, we've made some decision, right? We've said, okay, we're going to allow this container to expand,
Yeah.
right?
Right. And then presumably at some point, you have the edge cases to handle. One of them is I'm done, I give it back somehow. Another one is I just asked for 100 gigs and 10x my size until I die out of memory.
Right, and you can see as part of this as well, we can explicitly pause the container, and then on line 522, you can actually roll the container into persistent storage.
Okay, this is like the you're going to pay in time.
Right,
We're gonna
and
kill
then
you. We're not going to. We'll say yes later.
yep, and then line 549, you can just kill the entire container, which immediately releases all of its resources.
Yeah. Okay. Now this is I like the design point. I think it's a good design point.
Well,
You
it's
can fit
an
things-
impossible problem.
Yeah.
So
It's not
any
impossible. It's just no one's thought about it.
no, it's I believe it's kind of an NP. Well, you know,
Not
it's one of
NP
those.
hard. No. It's somebody at the end has to decide what is the order and who loses.
That's right. Somebody there can be conditions where there are losers, and part of the problem is as engineers we never want there to be a loser.
Yeah.
So we spend inordinate amount of time trying to pretend that we can
That there are no
make sure
losers.
that no one ever has to die.
We're
And
all waiting in the line politely for our turn at the limited
That's
pile of
right.
resources, which I think is a fine, typical, best throughput answer. But also there are times when there needs to be a loser and we need to know how that decision's made so we can plan around
Right.
what happens to the loser. The loser got killed. Well, maybe he got restarted later. His job hierarchically gets pushed back uphill as out of resources, and that pushback rolls backwards through the pipeline of resource demands till somebody at the high level says, okay, I'll stop now. I'm overcommitted here.
And in an interesting way, remember I said I really loved Joe Duffy's writing on the error handling, but didn't agree with his answers.
Yeah.
And this is kind of like a similar concept. Like when we tried to design this API, you know, the idea was, you know, we can't fix all the problems, right? But what we want to do is to have a very carefully designed point at which we can at least have a chance to answer the questions, so that if we do decide on a certain path to solve, for some meaning of
Yeah.
solve the problems,
Right.
there's a predictable outcome.
Right. No, that design methodology is great. I'm with that one. I don't, it's the difference between saying, I'm not looking at it and then it crashes how it crashes versus we are carefully declaring that we're out of memory and you get to die. And I don't know what else, you know, maybe there's a better answer than you die, but at least we know here's the decision point. And some future date, we may change how we die to stalled on disk and reran or restarted your transaction at a higher level, blah, blah. There's an infinite pile of how you want to handle best throughput, but there is a point at which somebody loses.
Right.
Is there a problem with people blocking forever
Yeah.
in some of these user callbacks? It seems like it has the same problem that finalizers have, where somebody poorly written finalizer blocks the queue.
No, because the blocking only occurs within a container. So if you're the parent container, you created that child container, you get a callback as the parent to do something. That callback occurs in the parent container. So if you block on that indefinitely,
that's the parent. That's the guy who wrote the callback. Yeah.
Yeah.
Right.
Okay.
The child
I mean,
cannot hurt the parent here.
you're allowed to do whatever you want inside your container, literally whatever you want, but you have no touch points to the outside world whatsoever.
So the callback was made. Where did the child get the callback?
The child didn't get the callback. So so going back to the, I'll tell you what, I'll share a screen.
Probably not crucial. It's fine.
Set it up so I can share a screen, and I'll walk you through some of this, because
yeah. Just a second.
we're definitely way off from the exception and future stuff. But
no, I think resource limitations are actually probably not what I want here. I want this. Okay, boom, 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 boom. Yes, fine. See if you get it now. I'm not.
Okay, here we go. Desktop 1. Good.
Okay. Yeah, fine.
I'm telling it to share.
Yeah, it's saying
All right.
it's starting. Dumpy.
So, let me just remind you that we have this concept of a service. So when I declare a class as a service, it implements this interface called service. I assume everything is coming through clearly.
Yeah.
And basically, a service represents a thread-like thing. It has at most one thread of execution occurring within it at any given time. So it's like a thread. It's like a Erlang process, I think is the term for those of you who've used Erlang. So it is something that's, GCable, shutdownable, killable, right? These are, and when it says kill, that's not a process that one can reject, right? It's a kill. So a container contains services, but a container is a service. So if we look here at the declaration of the container itself, I'm a little bit slow on the mouse. A service, I say service container. So that makes this class, this container class, as a service. And you can see that it delegates all of its control API work to some reference. It has some property called control. That's where you see this. And the reason is that when I create a container, it actually has two services. One is the outer service that the parent has a hold on. And then one is kind of when it starts up, it has an inner service that's actually running inside the container. So the control surface area is on the surface of the container and thus outside of the container. The execution within the container starts on the first initial service created inside the container. And this solves some of the problems if you go back 40 years to how do you start a process in an operating system type thing. It's kind of some of the same things that we had struggles with back then. But basically, it gives you a control plane that's outside of the container and then kind of an initial, think of it where the main runs inside of the container. That's a C reference. We don't actually have a main, but it gives you the idea. So then when you create the container, it pretends that it is its own control interface, right? So this delegates means it implements it, but basically, unless it's overridden, every method just goes directly to whatever that reference is. So read this as implements plus boilerplate, if that makes sense. So now, what does that control interface looks like? Well, we already saw some of it, which was the GC and kill and so on. This also provides a status of the container, and it allows you to set a target optimization goal for the container. So we simplified this down to kind of brain dead simple. And the reason is, again, going back to the user mode concept, you don't want the user mode involved with these decisions, right? So you want to set kind of high level goals and then let the actual code generation or the runtime do whatever is best to accomplish it. And I'll kind of point to some examples of where it was really hard to get this right in previous things you may have worked with, like thread priority, either at an operating system level or say thread priority in Java. How hard that was to get
Java
right.
were broken, so just you skip them. But OS priorities.
So for example, scheduling priority, if you look at this comment, this comment took probably 2 days to write. And that's because this is that type of problem, right? Which is how do you indicate priority when you're trying to indicate it as a relative priority to other things, but you can't actually see those other things, right? So it's
can't do it. You can't see them.
Right.
Well, you see them as much as they exist, and then also they have a priority. So picking a number here for scheduling priority is exactly the guy who pays money pays for it to be a 1.
Right.
It would be less than a 1.
Right.
Yeah.
Exactly. So did I answer the question? Because I can't remember exactly what the question was, because I get talking and then I forget what I was talking
Yeah,
about.
I forgot to. It's all good.
I think we had so many questions and things come out of that.
Oh, I was trying to sort out how you voted, which way you wanted to vote. What was your methodology for choosing how the votes happened? What I see is there's some goal thing, which is a generic voting strategy that encourages people to pick things that have good throughput, but at the cost of whatever. There is a CPU scheduling priority, which I assume that's what priority is, actually CPU and not memory, which says something about I can pay money to get a higher or smaller number. Somebody's picking. The guy who picks that number, fights with other guys who pick that number, and there's some marketplace between them, and there's probably user writing. So some user says, I want this, and his manager says, it's a 1.
Right.
What do you do with, for instance, memory in terms of priority? I lose, or does priority include memory? Like
Nope.
Okay.
So the memory, it goes back to that callback concept where you say, I'm letting this container use, so from the outside, I call limit memory. So on that surface plane, I say that container, I want to limit its memory to this many bytes, right? That's the max. And it's like, don't bother ever calling me back if they don't exceed it. But if they do exceed it, tell me.
This is the parent gets the callback from the child container.
That's right. So because I'm providing a function callback, when that gets called, it happens within the context of that function, which is its parent container.
Right. So now if the parent container is being told some child container is out of memory and the child container is of low priority and he has some spare memory, he makes a decision. And if the parent container gets called from a child and the child container is the max priority, whatever that means, and there's not enough memory to go around, but he has a bunch of other children he's running, is he, going to kill, or what's he going to do? Well, this is the user code. So now what I'm asking is, how is this design decision implemented? You're allowing a programmer of the higher level container to decide how best to split resources among lower level containers.
Right. And until that parent container calls back in and either says limit memory or kill or whatever, that child container is effectively frozen.
Yeah.
It makes no progress.
Got you.
So that gives you 3 choices, right? Approve, kill, or wait. So basically, you're always going to be making one of those 3 choices. Wait is basically do nothing.
Right. You could give the child another option that says, this memory is give me a memory allocation that can fail. And so instead of failing out, he'll just take the null on malloc and then do something.
Yeah, we haven't considered that.
We on H2O, that's how we did a lot of the recovery. The theory was that any minor new blah, blah, blah would run you out of memory. But in practice, what happened was that there was a big one that came along and he lumped you out of memory right away. And all the big ones were tied to doing new allocations of large data structures having to do with the math you're doing. So those all went to this special route, which would attempt, fail, catch an out of memory, decide it wasn't going to happen, and begin the recovery of the math process at that point, saying, it's not going to work. And the little guys would throw out of memory, and we didn't have a good, we had a fakey answer, which was we actually kept a little bit of memory, some fractional memory set aside in a big fat array. When a little guy failed, you caught out of memory, you freed the big thing, you set all your flags, said you're going to abort at your next convenient abort point. Right. If the little guys kept allocating little things, you were dead and it failed, it didn't work. But if they then detected soon enough, wherever soon enough was, before you ran out of your pad memory, you could recover. And the answer was, it kind of sort of worked most of the time.
Yeah, and part of the challenge is how do you build those abstractions so that people who aren't named Cliff Click can successfully use them?
Right. So the math
Because this is, can I rant for a second?
built.
Because you have these you have these people who write books and they're like agile or extreme programming or whatever, and it's like, okay, you give me Kent Beck and 12 other Kent Becks and I can build freaking anything, right? Like, you give me these people who write these books, like the reason they're writing the books is like they've already succeeded doing something. Like, my problem isn't that I have 12 Kent Becks that I have to get to build something. It's that I have 80 people fresh out of college, and they're brilliant. I love them, but they're not.
Right, I get it.
They haven't already done that. So it's like, if I give Kent Beck waterfall method, he's like, no problem, I'll build it with that. I give him extreme programming, he's like, no problem. It's like,
yeah. So I claim that we could have mathematicians write code because their form of allocation was always, I made another giant array, and that worked. And then to actually implement the system, I had to have systems engineers that I got to train and work through. And that was a dozen Kent Becks, or trained up to be Cameron Purdy training up your 20 guys. You're going to train them up and they're going to figure it out. But you don't need a huge count. But for use outside of your small coterie, you need to have some defaults that are sensible, that somebody's just going to say, oh, I'm going to take max throughput, or I'm going to say, no, this is the high priority task. And he's going to want to have a one button push for a couple of choices that you can implement.
Yeah, and generally what you don't want to end up with is a system that allows itself to get into a state where it's spending all of its time trying to make progress and failing to make any progress.
No. There is a yes. That was beaten into my head watching Java and GC as you
GC with
approach your OutOfMemory.
Well, or GC when any of the memory is in swap, right?
Yeah, and GC and in swap too. That's correct. So are you done with sharing here?
Yes, let me stop share.
Your video of your face is
and what I'd just say,
my neck was getting hurt.
What I'd say is that API we were just looking at, it was kind of based on this idea that, and I've written about this somewhere, so it's probably on our blog or something, but this idea that when you create a container, it's kind of like God creating the universe, right? Like this term faith, like, I've never seen God, right? I don't know if God exists. I can't know if God exists. And actually, that's because he's outside the universe, right? So it's like when we create a container, it's like God creating the universe. You can't say that God exists, right? But the universe exists, right? So that API was the way that, if you will, God could poke something into the universe. So when we say, for example, I need a file system, right? We hold out our hands and we pray for a file system, and God from outside the universe puts a file system there, right? That's injection. So resource injection into a container, for example. And similarly, you can think of running out of memory as I need memory, except you're not smart enough to stop and ask. You simply say, glue these two strings together, and behind the scenes, your universe gets frozen. Someone runs off to God and says, hey, God, that universe over there needs a little more memory, right? So it's this, if God gets tired of that, he just kills the universe.
Right. No, I like the model in terms of the resource management being hierarchical has a huge advantage over the hierarchy is one deep and the process dies, right? You do get to die it at different levels and then do some sort of sensible recovery. I think that's a great answer.
I like the model, but don't you run into the problem of the users now needing to be smart enough to write this so they're not constantly battling, right? So the example I'm thinking of is I have a container, and inside it I have two containers, and let's say I have 100 gigs of memory, and initially I want to give both of them 50. One of them grows to be 60. The other one wants to grow above the 40 it's allowed. So I try and limit the first one back down to 50, so I can let the other one succeed. And I'm going to keep toggling back and forth between these two, calling into max RAM exceeded, asking for more.
So generally, you're only going to call into that that limit function when one of them has exceeded its number. And the idea is, if, let's say, go back to Cliff's point that it's about who's paying for it. Let's say they're both paying for it. And at that point, it's like, I can't grow these both to give them what they want. So I take one of them, I make some choice, I take one of them, I write it out to
Yeah.
storage. And on another server, I read it in and continue it from that point. So I can actually migrate the container.
My take on that one was you made a mistake when you promised them both,
Correct.
and you shouldn't promise them both. And the
It's a calculated error.
The Azul solution was you can borrow some memory to run more efficiently. You have a hard ask. I'll grant you, you won't be launched unless I can give you your hard ask. But if at any point in time, I want you to shrink back down to your hard ask, you have a fixed time budget. I'll do it for you behind your back by poking the GC. If you can't make it, you failed because you exceeded your hard ask. And that's how the losing decision is made.
Right, but with this model, if that's a user written callback, that max RAM exceeded is a user written callback. If I understood
but
that
that's
correctly.
the user of the
Yeah.
user. It's user code, but it's not the same user code as wrote the app. Typically, it's that
Is the intention there, Cam, that those user callbacks are like write a scheduler, right? Of which there will be 4. Not
like
Joe Schmo uses them.
Right. Somebody's writing a scheduler. The Azul had a particular callback schedule baked in, which if you called the limit exceeded, the callback was at your launch time, you got a guarantee. You're now exceeding your guarantee. We'll grant you up to whenever we want, but at some future point, we may revoke that grant. So it's a different model that you don't get to raise your hard ask. If on the other hand, the Azul, you could do the hard ask raise in the Azul side, it would work. It just means we refuse to let the sum of hard asks exceed our memory.
Yeah, and Dan, just to answer your question from a different angle, we all that stuff I showed you is like built into the language. It's not all implemented yet, but it's all built in and designed into the language itself, language/runtime. The reason we did it is we actually planned as a business to build an implementation that would host other people's applications, and to do that, we need to be able to manage their resources. And most of those applications will host for free. So we need to be able to efficiently stuff way more onto a machine than is theoretically possible in a LXC or Docker world. So so in those cases, though, we also get a lot more leeway, if you will, for not having them respond within 1 millisecond.
Right. You're in there for free. You get the free model, which is I can pause you at any time. It's batch throughput goodness. It's best effort, blah, blah, blah. You get killed and restarted, whatever.
Right. But, with that said, I mean, it's not that we plan to deliver horrible service. It's that we need flexibility.
Yeah.
So,
yeah, I was thinking more in terms of the, people writing the equivalent of today's app servers with this model.
Right. Yeah. And that's what we're writing.
Your app server developer is going to be hacking on some of this too.
Correct. Absolutely. And that's a very good way to put it, actually, Dan, because there'll be 20 app servers, but there'll be 20 million apps. So it is definitely a specialized area, writing a scheduler or something like that.
Yeah.
And by the way, we're not, user mode doesn't do the scheduling, so I shouldn't have implied that you're actually writing a scheduler. You're writing something that answers questions when resources get previously approved resources get exceeded.
Right.
Yeah.
And now, what more resources do you grant, and who gets it, who doesn't? And the issue with memory is typically the guy asking memory cannot make progress without getting it.
Correct.
Whereas with CPU, you can stall in a fine-grained fashion, and he'll get less and less as he distributes the CPU among friends. Classic CPU sharing.
Right.
Yeah.
And so your outermost container is kind of like the old DOS com files, right? You know, when the outermost container starts, there's probably nothing outside it in user mode making decisions, right? It's like, I don't know if you remember, but the first 2 or 4 bytes of the com file, you basically said, how much memory do I want? And all you did was F, however many Fs it would take. You
Right.
basically said, I want everything on this machine, right? But then within that, you know, you're running potentially thousands of concurrent applications. So now you, as the thing that took as much as you could from the machine, now you're responsible for now doling that out in smaller and hopefully dynamic pieces.
Yeah.
So
That'll be an interesting piece of code for people to write, to be able to make those decisions and make them fast enough to not destroy somebody's quality of service.
agreed. And the other thing I keep trying to remind myself, sometimes unsuccessfully, is that the challenge that we have now isn't so much, you know, make each piece of code fast enough. It's design things so that I can actually never get stuck just running one core, right? It's a
Yeah.
because you look at some of the mistakes made by various operating systems and stuff, and what you'll see is occasionally when things get bad, you know, you have one core that becomes the limiting arbiter for the rest of the system. So for example, with a thread scheduler, it's a single threaded problem, right? Or so on. So that's why we tried to break everything down hierarchically, because it allows you still fundamentally have one root that can't scale, right? But you're trying to push mess down the hierarchy and say, deal with it down there. Don't come back to me. So we'll eventually find out if it was a good decision.
We went a long time at Azul looking at common sleep wake up patterns in Java, where some resource returned with a value, and then you had to wake up 100 threads or 1,000 threads, and we had a 1,000 core machine. And the usual wake up pattern was the JVM said, wake up this guy, wake up this guy, wake up this guy. And they all immediately went to go grab a lock because it was a wait notify. They all got notified. They're all grabbing the lock, do some trivial thing, and now they can run. But they all had to take the lock and turn. And so that was this giant bottleneck at getting things started from a scratch. But we had the cores, but make them actually go. So as soon as you had a wait notify pattern with 1,000 cores on it, you know, the wake up time, because 1,000 guys didn't compete on a lock. Well, the competition time is so slow, many of them don't even spin enough before they give it up, and they want to go back to sleep again.
Right.
And
Gil just posted the other day something about, you know, anytime he sees notify all, it probably means it's a bad implementation.
yeah, but it was a common thing. Right. I don't know what the right answer there is.
And just for context, Gil is the Gil Tene is the CTO of Azul, and not the global interpreter lock.
Yeah, wrong Gil. But he's a smart guy and does some cool stuff with latency calculations and big system load math and stuff. He and I went toe to toe for a long time.
So I want to get back on the exceptions one, because I was learning stuff and also had I had a comment I wanted to make earlier, which was one of the biggest problems I've seen with exceptions is most of them are not exceptional. And so I had this old saying that I use, which is exceptions should be exceptional. And you know, if you ever look at a production log, and we have, you will quite often find terabytes of exceptions happening over and over and over again. And all that happens is they end up getting flushed to these logs, and they're terribly expensive, and so on. So going back to the Midori conversation and so on.
Put a link for Midori in the chat.
I did the Joe Duffy blog. That's Midori.
Oh,
that's the Midori blog.
That is the Midori blog. Okay, fine.
Yeah. I don't think they ever shipped anything. That was a
it's
Microsoft
like a
research
project.
Fine.
So I was curious though, York, from what you were saying, like how much does that concept apply, that a lot of the problems that people are dealing with where they're using exceptions shouldn't be exceptions?
I'm happy to
Right.
talk about that one.
Yeah, it's It's interesting because you mentioned the logs. I just, in the meantime, popped open the error monitoring for GitLab.com because I know we have like tens of thousands of errors there that nobody ever looks at. But to illustrate, probably one of the most common one is a HTTP timeout from some service we probably use. There's currently basically 290,000 instances of that recorded.
Right.
To be fair, those are timeouts.
Right.
Yeah, but why did you bother logging them?
Right, that's the thing. And so
I'm just thinking about the amount of time that went into 290,000 timeouts.
and that's the thing, they're pretty expensive to produce on Ruby too, because every timeout is a full stack trace.
Well, they parallelize well on the other hand.
Well, it's Ruby. It doesn't run stuff in parallel.
So I have this rant I do on exceptions that are not exceptional, and the answer for me has typically been somebody catches it, decides they don't know how to handle it, they've never tested their handling anyhow, so it's buggy in hell, but they log it, they strip other information like the stack trace out of it, and they throw again.
Right.
So it's expensive, it's slow, it's broken, and it was useless. If they hadn't caught it, it would have been fast, and we'd gotten a real stack trace out of it.
Right.
Fine.
Yeah. So in my case, I am very much leaning towards basically if there is no sane way of handling this at runtime, it should not be an exception. It should be a panic, a hard termination.
Oh, okay.
Because
That's
it's most likely a bug.
Duffy, yeah. Abandon all hope, all ye who enter here. Yes.
Essentially. And currently I have some mechanism that you can respond to that. That's mostly actually used in the unit testing code. So that you can test, hey, this method panics without it terminating.
Let me tell you about writing unit tests for Java out of memory when you're running all these other tests, hopefully in parallel for fast effort.
Yeah. There I am considering ripping that out and eventually replacing that with basically just spawning a sub OS process and just checking, hey, did that exit with exit one?
Yes.
But I currently don't have facilities for spawning OS processes, so it's not an option yet.
Okay. We went round and round doing out of memory testing, and then watching the other tests fail for out of memory. They're unrelated to out of memory because the out of memory guy was running the system out of memory as part of his test. That had to be fixed at the process level because that was a process level resource consumption. So you had to do a process level thing. The other one that was a great fail mode was the things that were testing limit cases of threads with yields and lock and wait notifies, which could lock a system up pretty hardcore. There were some poorly written tests that turned into live locks that would drown a machine. Basically, once you got past 8 more threads than you had cores, the internal OS scheduler wouldn't ever give time to runnables beyond 8 per core. So you had a 4-core system. If you had 32 runnables, they all took a turn. If you had 64 runnables, 32 took turns and 32 never ever ran, including the ones that the test is done, we've timed out, the test is done, I'm setting the flag saying the test is done that everyone will pay attention to. So that one would starve to death and the machine would halt. And then you couldn't even log in because the OS wouldn't let the user SSH shell to run, and you couldn't get a control C in there sideways and all that kind of stuff.
Yes.
So all those,
so-
of course, limitation tests were a pain in the neck.
Yeah, and so there I am generally leaning towards abandonment basically being the default.
Yeah.
I mean, there's nothing that necessarily makes it the default, but sort of a philosophical approach.
Yeah.
And then for like errors itself, most of them are just the same error type. So there's a type called standard error, and it just provides a message. That's it. The underlying idea there, a pattern that I've seen very often in the code that I work with, is people define some sort of class or whatever, and they add an error type for it because the class needs to throw an error. But all that error type does, it just provides a name to the error. That's it. It doesn't have anything else meaningful. And so you basically end up with thousands of exception classes that only differ by name.
And you have to catch them all.
Yeah.
Or
and so in my case,
catch all, whatever you do,
right.
the default top level catch all.
And so in my case, the language itself, it already restricts you to throwing one type. Like you can't throw two, just one.
Okay.
You can throw an interface, but then you're sort of restricted by whatever that interface provides. But it also means at the catch side, you only ever have to worry about one type.
Okay.
And then through that, I figured, hey, if you're going to do that anyway, why not just use the same error type for all things? Because
Right.
most of the time, all you need is a message.
Yes. Yes.
And then I went a step further and basically said, let's get rid of stack traces. As in, they are not produced unless you implement a custom error type that does. And that works because it's all explicitly handled. So you have to explicitly throw it up. And setting aside bugs in the compiler,
Well, if
they
I'm throwing a panic error, I want the stack trace.
right, those do have
Okay.
stack traces, but let's say user provided exceptions don't.
Uh-huh.
And that's because they can't be implicitly logged anywhere anyway. And if you handle them explicitly, so if you have some code saying, take this error and log it, I'm kind of the opinion, like, why not just handle it? Like, why are you
Right.
logging an exception? Because that means it's not exceptional.
Yes, that's my. I've been going round and around what the hell do there, and one of them is, if you're going to handle it, you should handle it, and you better handle it all the way and not log and rethrow, because the next guy up will log and rethrow anyhow. So why the hell are you logging?
Right.
Yeah, very few people should be catching.
Very few,
Right.
yes. Very few people, yes. If you cannot handle it completely. So if you're writing a top level service like Cameron's model is, the top level service guy should be able to catch and handle by defeating, restarting the low level service or whatever he's going to do.
Right.
But other kind of exceptions, usually the people catching have no business catching, have no way to handle, and they should be told, thou shalt not catch unless you're going to totally
Right.
handle.
I also have a much different opinion on the cost of building a stack trace, because I think it's actually very close to zero.
Okay.
And I mentioned this to you before, Cliff, I think.
I do profiling on stack traces where I get the cost very, very close to zero.
So when you look at, so the example we were talking about just a few minutes ago with the 280,000 Yorick, what was it, 280,000?
Yeah,
right.
288 to be exact.
Yeah, right.
You know, I would guess that there's probably 5 different stack traces generated close to 100,000 times each, right?
I have the tail suffix all identically and a little bit of leader in the middle messed up. Yeah, fine. Yeah.
So this is where you can basically hotspot your I'm not kidding. Like you keep a small amount of statistics at the call site, i.e. the throw site.
Yeah.
And, and after a while you say, it's going to be worth doing some statistical analysis on what generates here, right? And you basically cache your most frequent throws. And so now your cost, let's say you throw 1 million a day, right? There's going to be
it's not going to count for anything. It's only 1 million a minute. You want to do something, 1 million a day.
Right. Well, whatever. Yeah.
There's a rate which you care.
Right. That's what I'm after. Yeah.
Yeah. Hotspot totally looks for common exception throws and inlines to the catch if he can. And if he can, then he turns it into a go-to under the hood, and he short circuits all kinds of things, including the stack trace can now be removed. Right. Otherwise, he builds it. And it's expensive to build it because he built a large Java visible structure. Whereas the profiling tool builds a stack trace by crawling the stack, grabbing PCs, and throwing them into a ring buffer. And after a while, the ring buffer got full. He hands it off to a background guy who processes those stack traces, finding a huge count of commonalities, which just what you said. He does some statistical analysis. He compresses them by removing all the common ones and just putting counters on them. And enhance the profiling a new empty buffer, right? So the profiling version of grabbing a stack trace gets in and out, and it's some modest kind of nanoseconds. It's crawl, but it's self-local, but you have to do a lookup on the PC to decide stack size. There's a little bit of screwing around, but it's under a microsecond for a stack crawl.
So the reason we started optimizing them or looking at a design for optimizing them was because of async. To bring us full circle back to the async await future conversation. Because if you have a caller that hits an async call, and then it transfers to the thing that's actually going to execute the call asynchronously, if that does a throw or wants to see a stack trace or whatever, you'd like to see where it came from.
Mm-hmm. Mhm.
And the problem is on that async boundary, you can't predict whether or not you need to maintain, do you need to keep the stack frames to produce a stack trace? Because the caller kept going. It's made 100 calls since then. Maybe it doesn't even exist anymore. That thread's gone, right? But the thing it called is still running, right? So now it does a throw. What's the stack trace? You need to go back across that async divide, because otherwise you don't know what caused the async call.
That's interesting. So H2O, we did a different story there. And I guess in theory, then I looked at what you just said and made a decision without realizing I made it, which was at the time I did the fork to the async call, I squirreled away a token, which was the call site, but not the full stack trace. When you threw, the exception was recognized at the get point, which you're required to have. So the get point was a bulk get across everybody who threw that you had this. It was a convenient, okay, but you got the stack trace of the get point, plus the suffix or prefix that came from where you threw. So you threw some range check exception. He bobbled across one cluster's worth of reasonable math. He had a cluster boundary. It got serialized, spit over. The other guy went back to his fork point because he was doing a parallel cross cluster call. You got a token saying that's the kind of place I was at when I forked it. But then the rest of the stack trace, the forking guy ran on until he had a block, and you got the stack trace from the block. So it wasn't the same. The other thing that happened to be there is that when somebody threw, usually had launched thousands, 100,000 threads, they all threw the same exception. I got 100,000 replicated variations of the same damn exception. So I rolled them up and compressed them that way. And you got a histogram of exceptions, the top 3 winners plus a count of total and yada, yada, yada. You had a bunch of stuff thrown in that. And it showed up as a Java exception with a full stack trace of the most favorite exception thrown.
I'm going to guess that's not what Yorick did.
No, so the VM doesn't produce stack traces at all until you tell it to. There's basically a method as part of the standard library that you can use to obtain a stack trace. And it's not used by any exceptions.
And that stack trace, is that a string?
Yeah, it's an array of somewhat more complex objects, but they basically contain the file path, the line, the column, and like a message.
Right.
So a message like the name of the block that it's basically in.
Yeah, there's a variation of that says do a profile style version, which is the cheapest possible stack trace that records things, but it's not user interpretable. And then there's, if you don't care for it, later you throw it away, it didn't cost much. And if you cared for it later, you said, okay, now barf this out into full.
Right. Yeah, and this functionality mostly exists so that the unit testing library can use this to generate a like a failure line if your test fails. That's basically what it's used for.
Okay.
But yeah, I would go as far as to say that all these services that exist to log your errors, or specifically your exceptions, they should not exist. They should be logging hard program terminations that you monitor using some system level service like Runit or systemd or whatever.
Yeah.
I've also thought that maybe the better approach is logarithmic, right? Like the first error, oh, wow, I haven't seen that one before. That's important, right? The 10th one, this is kind of important, right? But it degrades to the point where it's like, okay, you've had 1 million of them. Okay, you've had 1 billion of them, right? Like
the problem is that you don't know that you have an extra one until you do some amount of work to recognize that this is actually another version of the same thing.
So we actually spent quite a bit of time at GitLab trying to look into this, because what we at the time we're doing, still sort of working on it, we wanted to have some sort of automated check that can say, hey, it's good to deploy to production, because we're still sort of moving to a fully automated setup. It's mostly automated, but in other words, we don't want to start deploying if the service is getting hammered already, unless we are actually deploying a fix. And one of the ideas we had is, hey, we want to deploy to a canary host first, then look at our error logging and see if, certain error counts have gone up and such. But we basically end up with the problem that there's so many errors is you can't decide which ones to look for. right? Even if you look at just a increase in total versus the last week, that could be affected by completely unrelated things.
Because I claim that you're clearing, somebody's claiming something as an error that's not really an error. It's,
Oh yeah, I would argue probably 98% of the errors that we log shouldn't be there in the first
shouldn't
place.
be logged at all. Yep. And what's this all written in? Is this
Ruby.
Ruby.
So
yeah.
you can throw anything anywhere at any point in time. We did some attempts at grouping them because we use Sentry for logging. They have some facilities that you can group related errors. It's the same thing. We had so much that everything becomes noise basically.
right? And I've worked with systems where this has happened, and I don't know how to recover from it. It's like somebody's got a programming mindset of throw for whatever, and then somebody has to catch and ignore.
I think this is mostly a symptom of a lot of, at least the more dynamic languages, not putting a lot of attention on error handling. They look at what exists, which is exceptions, and say, oh, we just also throw exceptions. That's it. And that's how you end up, I think, with these, stack calls, call stacks, where you have, 10 calls deep, it throws something, and it just magically bubbles up somewhere.
10 calls deep. It's 100 calls.
Or 100, a million, whatever it is. But you end up with this point, it's like, hey, let's say we want to handle all the exceptions. Well, theoretically, you have to handle out-of-memory errors, syntax errors, because Ruby uses exceptions for those. The 15 different exceptions that you may get from interacting with I/O. It basically reaches a point where basically anybody says, you know what, screw it, I'm just not going to do it. Make it the problem of basically the next person. But that's why I'm such a fan of the Midori approach, where they severely restrict that.
Yes.
And I kind of like tighten the screws even a bit further, which I think if you're not used to it, I think you get sort of a culture shock experience where you're like, whoa, this is really different.
I want to hear. Yeah, I want to hear what the what the feedback is kind of down the road. I'd love to hear how.
Yeah, so far I've seen people being positive, but it's hard to say if that's because it's truly a good idea or if they just glanced over it and haven't really, gotten their feet wet with it.
Yeah.
Well, and the other thing is sometimes we react to what we know. So, for example, if they're in a similar situation as you are, where they're dealing with millions of things that shouldn't be there, maybe they're saying, this is really worth it. And so it's kind of a reflection of the problem that they're currently facing.
Mm-hmm. Oh, no, exactly. And it's, I think my biggest issue there thus far has been that you can very much do things with the language, but unless I think you're interested in the actual development of it, there's just too many bits and pieces still missing. Like simple things like I don't have any functionality for spawning OS processes or even creating SSL sockets. It has socket support, non-blocking and everything, but every time I look at how to integrate SSL, the libraries used for that are generally very invasive. They sort of want to wrap themselves around the sockets.
That's one word for it.
and that model ends up not working very well when you have a runtime, your own I/O polling logic,
right?
That sort of thing.
No, it's particularly complicated when you're trying to integrate SSL in a non-blocking manner. So,
yeah, I have to head off in a couple minutes, but with that, I've even briefly considered, hey, you know what? Maybe I should just write it in the language itself. And then I basically did the double text, like, no, no, never. Like, I need a lot of alcohol if I want to write an SSL library.
It sounds like a lose-lose situation, because I'm fairly certain if I write a lot of complicated code with a lot of alcohol, it does not. The next day, it's like, what the hell?
Well,
it works. I just don't remember why it works.
You do a code review the next day. Code review your own code.
Yes. I've tried it a few times, and the end result is not pretty.
No, and it's I briefly looked into this again a couple of months ago, and I was like, okay, hey, maybe there are quote unquote simple C libraries that I can perhaps use as a reference and perhaps port them over. But they all
So you're
started
saying
like
you need a non-blocking version of SSL?
no, not necessarily, because I think OpenSSL, for example, it does support non-blocking. The issue is that currently the VM has a built-in socket type, and that wraps a basically standard Unix socket, standard POSIX socket. The trouble is that OpenSSL, for example, you essentially use one of the functions and you get back this sort of wrapper around a POSIX socket, but it's not the same type. And then they have all these functions that you have to pass it through to do the handshake, get the data, etc. You basically end up with at least in your runtime, having to implement 2 different socket APIs.
That's
one
correct.
Non-blocking regular ones and one non-blocking SSL.
Right, because the establishing the socket is dramatically more orchestrated with SSL than with TCP.
Right. Yeah, and that's where I've been leaning towards. Hey, in theory, if I basically 10 CAN-BACKs, I could do that in my own language, because then it wouldn't be you wouldn't have these 2 duplicate implementations. But that's yeah, I don't know. I think it's a bad idea, at least at this time. It reminds me, as a closing point, I think a year or 2 ago, I read this article about somebody who, some programmer in the 70s or something, he was suffering from burnout. And he'd read how LSD can be effective in promoting productivity and such. And so he experimented with microdosing and kept record of it. And then a couple of years ago, wrote a paper about it. It wasn't really scientific, but and his experience was basically, in the moment, it was great because I was very productive, super focused, etc. But then the next day I hated myself because I could not understand what on earth I had done. I mean, it worked, but it might as well have been hieroglyphs, essentially.
So was that Larry Wall by any chance?
I don't think so.
The guy who wrote Perl, obviously. Yeah.
Yes.
Yeah.
Oh, I've met him before. He would fit the prototype.
Perl, Raku definitely is an indication of let's just put everything in there that we can think of. But yeah. No, anyway, I have to drop off.
Yes, let's wrap it up here. Okay. Anyone have any comments they want to throw in before we close off here?
I got to tell you, I would not mind further discussion in the future on good ways to handle exceptions and error handling. This is
exceptions and error handling. I'm happy to do that.
It's always it's always a topic.
Really good conversation.
Yeah.
I'm sorry, I'm trying to make bad puns here. If you don't get it, it was a really bad pun.
I didn't catch it.
Good. Let it die. All right, next week, maybe we'll talk exceptions. Have an exceptionally good week. Try it again.
You too.
Bye.
All right.